I'm going to just quickly review some of the stuff from Chapter 7 and Chapter 8. So this was Introduction to Discrete Random Variables, Introduction to Continuous Random Variables. The two subjects are very similar. What's the biggest difference between continuous and discrete random variables? Or at least notationally, what's the biggest difference? Integrals versus sums. If you had your choice, which would you rather do? Integrals. We have classes on integration. We have techniques of integration. We don't have as many techniques on sums. We would much rather use continuous random variables. Later in the semester, I will give a lecture on applications of probability and multivariable calculus to baseball. Those of you who have taken Calc 3 with me, it is almost entirely the same lecture as what you've already heard. All right? The only difference is I will not be using the previous Red Sox season. Continuous random variables are much easier because of what result from calculus. What's the big result from calculus that helps us? Fundamental theorem of calculus, which says that you can convert a lot of these integrals to just evaluating the antiderivative functions at special points. And the reason we care about this is integrals give us areas under curves. Areas under curves, at least for continuous random variables, are probabilities. So that's why we care so much about this. All right, so Chapter 7. So this is Intro to Discrete Random Variables. And so in the interest of time, we will use the letters RV to denote random variables for the rest of the semester. The other phrase which we will eventually use is IIDRV, independent, identically distributed random variables. Essentially, things are as nice as possible. You have a bunch of random variables. They all follow the same rule, and they don't depend on each other. They're all independent. So IIDRV will be an expression we'll see a lot of times throughout the semester. Right now, it's just RV for random variables. So the other abbreviations is PDF for probability density function. And we often use instead maybe PMF for the probability mass function. And you should think of this as associating a probability to a discrete set of events. It has to sum to 1. It has to be non-negative. So xn is at most countable. Then you'll have the sum of px xn equals 1. Px of xn is greater than or equal to 0. So I'd never assign negative probabilities. All the probabilities have to sum to 1. I like to use a subscript to denote the random variable I'm talking about. If I only have one random variable that I'm discussing, I don't really need this. This is overkill. But when you start having multiple random variables going around, it's really nice if your densities reflect the variable you're talking about and just have it coded there. The next is the CDF, the cumulative distribution function. And the CDF is a little bit harder in the discrete case than the continuous case. And so what we'll often do is use lower cases for densities and upper cases for CDFs. This would be the probability that x takes on a value less than or equal to x. In the continuous case, we don't have to really worry about is it strictly less than x or is it less than or equal to x. In the continuous case, the probability of a singleton is 0, so this doesn't matter. In the discrete case, this is extremely important because everything is discrete. Singletons do have probabilities. And so we have to be a little bit more careful as to what we mean. And there's a lot of properties you can say about this. As x gets very, very large, the cumulative distribution function approaches what number? 1. And as x goes all the way to minus infinity, it approaches 0. OK, so these are the two fundamental properties of the cumulative distribution function. Another big one is it's non-decreasing. The probability that you're less than or equal to 4 is going to be less than or equal to the probability you're less than or equal to 5. As I increase x, your probability doesn't get smaller as you go. It's like a running tally as you walk down. And it turns out the CDF is very useful. It's more useful in the continuous case because of calculus. The derivative of the CDF is going to be the PDF. This will allow us to convert from one random variable and its density to another random variable and its density. So the CDF is going to be a wonderful tool for calculations like that. Last little bit of notation, we usually use capital letters, as I remarked earlier, to indicate random variables. Lowercase letters are the values they take on. And so here we're talking about the random variable x taking on a value at most little x. Okay, and then there's a bunch of examples you can do. I strongly urge you to read very carefully the example of the sum of two rolls of a die. This is a really good problem in terms of calculating the PDF, calculating the CDF. If you're willing to do some work, you can actually get a nice clean formula. And this is the formula I have with the absolute value. You have to play with it a little bit to see why that's true, but you can get a nice simple formula. You're not always able to do that. And as you add more and more things, it's going to get harder and harder and harder. Fortunately, the saving grace in the class is the central limit theorem, which says that in most circumstances, as you keep adding things together, there's this incredible smoothing that happens and this incredible universality, and the limiting behavior is almost independent of what you started with. And that's going to be one of the big results we'll be proving this semester. All right, so this was the Blitzkrieg introduction to Chapter 7. All right, Chapter 8, what's the difference? It's now intro, continuous random variables. So almost everything is the same as what we did. The main tool is the fundamental theorem of calculus. Okay, anybody who's taken Calc 3 with me, you're on the spot right now. If you're going to define the fundamental theorem of calculus, what rule, if you're going to state it, what word must be in your statement of the fundamental theorem of calculus? Area. Okay? Forgetting to say area when you talk about the fundamental theorem of calculus is worse than showing me the beautiful catch the Giants made in the 2008 Super Bowl. So if you really want to get me upset, this is even worse than what US Air did to me. Do not say the word area and see what happens. Okay? If you don't say the word area, it's the fundamental definition of calculus. Right? What is calculus? Well, we have some function big F of x, and we have little f of x is the derivative of big F of x. And if I integrate from a to b of little f of x dx, this is big F of b minus big F of a. This is not the statement of the fundamental theorem of calculus unless I say this is the area under y equals f of x from a to b. If I don't say this, this is essentially a definition. This is why the fundamental theorem of calculus is so useful. If I want to know the area under a curve, which is going to correspond to probabilities, then I can use calculus and relate this to finding antiderivatives. The big lie in Calc 2 is that you can find antiderivatives. We have to work really hard to come up with functions that have nice antiderivatives. Fortunately, there are a bunch of them, and a lot of them actually model a lot of processes in the real world. We got lucky. So that this idea will be useful, because we will be able to write down good expressions, nice closed form expressions for big F. But there will be several times that we will have trouble. All right, so what I want to do now is I want to move now to Chapter 9, expectation. So I'm going to start with the definition of what we're going to be looking at, and then I'm going to try to review some things from Calc 3. So x is a random variable with density f of x. Now, one of the annoying things in the subject is, am I talking about a discrete random variable or am I talking about a continuous random variable? If I'm talking about discrete, I should be using sums. If I'm talking about continuous, I should be using integrals. I don't want to be writing down every formula two different ways. So what I'm going to do is I'm going to overload the notion of an integral. And I will write down the integral. It's going to be fairly much the same if it was a sum. If you want to get technical, you can get into an advanced analysis course and talk about a discrete measure that you're integrating against. But I'm going to just use the integral notation for everything. You've hopefully seen this before. In Calc 3, if you talk about the length of a vector, do you use just absolute values or do you use pairs of lines on both sides? What did you guys use in Calc 3? So you guys did pairs of lines? Did anybody just do one line? Anybody do just one line? In linear. Okay, linear. Did you use just one line for linear, for length of a vector? Was it confusing that this was not the absolute value? I mean, it's nice when you see two lines here, that flags it. Good notation is valuable. But with a little bit of training, you realize, oh, okay, well, especially if they have an arrow over here, this is probably length. And so we just overload the notation a little bit. And so rather than just using the notation of double lines, we just say, let's generalize the notion of absolute value to be the notion of length. And we can take the absolute value of a number, which is the length of a number, or we can take the absolute value of a vector. It's the same thing here. I'm going to just be using continuous notation, integral notation. You should really talk about a similar thing in general. So now, the expected value of some function g of x is defined to be the integral from minus infinity to infinity of g of x, fx of x, dx. And again, if we had a sum, we would have, if we had a discrete random variable, we would have a sum. If exists. So the problem is, just because I write down an integral does not mean the integral makes sense. This is a very different question than, am I able to evaluate the integral? A lot of times I can write down integrals that are finite and converge and exist that I have no idea what they are. Right? If I gave you, for example, the integral from minus infinity to infinity of e to the negative x squared over x to the fourth plus 100 dx. Does this integral exist? Does this have sufficient decay?
Isn't it impossible to integrate e to the x squared?
This is the question I'm asking. I'm not saying, can I write down what it is? I'm just saying, does this integral exist? Is this a finite number? Yes. I have enormous decay. I have beyond exponential decay in both directions. I also have a decay of x to the fourth down below. I never have to worry about dividing by 0 because I have the 100 here. I have plenty of decay. When you have integrals like this, you often want to check, is everything well behaved near 0? Is everything well behaved in infinity? How quickly is it decaying? It's decaying faster than 1 over x to the fourth as I go off to plus or minus infinity. Or even better, it's decaying faster than e to the minus x as I go off to infinity. This function has enormous decay. This integral exists. What it is, no idea. Okay? I can't evaluate it, but I at least know that it exists and it makes sense. So a lot of times I can write down this formula for the expectation. And if you want, think of it as, x is your random variable. What would be the simplest choice for g of x that I'll let you get away with? 1. All right. What's the one I would not let you get away with? 0. I'm not going to let you get away with g of x equals 0. All right. If you take g of x equals 0, that's too easy. But let's take a function of the random variable. Let's make it 100. All right. So the random variable x is the work you do on the exam. And I'm going to just assign everybody 100. Okay? And I'm going to calculate expectation. What do you think I should get? 100. Everybody's getting the same thing. It's a constant. And so if I put in 100 here, I can pull that outside the integral, and now I'm integrating my probability density function. So to get in this case, it would be the integral from minus infinity to infinity of 100 f of x dx. So I pull out the 100. Oh, I haven't told you what the distribution is. Do you need to know what the distribution is? No. What does it integrate to? 1. So there we go. It's 100. Okay? So this is how we would calculate the most basic expectation. Of course, we're going to want to allow ourselves to have more complicated g's than just g of x is constant. It is not that hard to analyze the constant function. Okay? It does not have that many mysteries. What do you think might be a better function to take rather than just g of x equals 100? G of x equals x. That will actually give me like the weighted average, the mean value of how well you do on the exam. And then what I would want to know is, what's the probability somebody gets a score of x? So do you think for the class exam I should be doing a continuous distribution or a discrete distribution? This should be a discrete case, right? I do not have anybody blurring in with anybody else here, right? Everybody is isolatable. Everyone is discrete. I'm going to get a fixed number, an integral number of exams back, all on time, all neat. And And so if I want to calculate the expected value, what I'm essentially doing is the following. What's the most natural distribution to put on you guys in the class? Uniform. I should treat all of you equally. I shouldn't treat the people who are taking this as a math class differently than those who are taking it as a stats class. Right? All should be treated equally. And so the most natural thing is everybody gets a mass of 1 over, I think, around 42. And so if I want to calculate the average value, what's the mean score on the exam, I can add up all your scores and divide by 42. Or equivalently, what I can do is for each person, I take the probability I chose that person, and then I multiply that by your exam score. Then I move on to the next person, and the next person, and the next person. And when I add that all up, that gives me the weighted exam score. But this treats freshmen, sophomores, juniors, and seniors equally. Is that reasonable? Where do we discriminate against sophomores on this campus? No. Housing, right? It's acceptable to discriminate against students by their year in terms of housing. Why? I'm sorry? Seniority, yeah, but why are we allowed to do that? I mean, we have all these claiming Williams days. Shouldn't we have claiming sophomore day?
Because we'll get there eventually.
You'll get there eventually, right? So we'll discriminate against you now, but then later on we'll let you discriminate against someone else. Oh, this sounds like a wonderful place to teach. So there's definitely situations where you would want to weight people differently. And so in the most natural situation, the easiest, simple situation is when everybody's weighted equally. But there will be some situations where things will be weighted differently. You might have people you care about more than others. If you're a manager of a Major League Baseball team, there are some very expensive prima donna stars that you have to make sure they stay happy. And so when you're trying to weight how much everything, not everybody is equal on your team. You place very well, you get certain benefits. So we want to be able to calculate quantities like this. And the idea is twofold. One, sometimes we care about these quantities themselves. And two, there are really good choices of G that will help us gain information about F. So F is the density we're trying to maybe either given or we're trying to understand. So good choices for G often take G of x equals x to the n. It's just raise it to the nth power. And this is going to lead to what we'll call moments. And so the moments of a distribution are extremely useful. And they are similar to things you've seen before. So moments. So mu n prime would be the integral from minus infinity to infinity of xn fx of x dx. So it's the expected value of x to the n. This is called the nth moment. Sometimes we'll look at mu n without the prime, which is the integral from minus infinity to infinity of x minus mu to the n fx of x dx, which is the expected value of x minus mu to the n, where mu is the expected value of x. And this is so useful, we give it a name and we call it, what do we call this? The mean. So there's lots of different notions of average value. The three big ones, they all begin with m, is the mean, the median, and the mode. The median is the place where half your probability is before, half your probability is after. The mode is the value that occurs most often. And the mean is the average value. It's the other notion of average. It's the one that you're used to. Add everything up, divide by the number of people. It turns out that the centered moments are actually a lot more useful for a lot of calculations. And a lot of this is because I can always adjust my scales. And so, playing these games to adjust, it can simplify the analysis to just shift everything back and standardize. So this is a good time to talk about why we define random variables the way we do and what we want to calculate. So I think we've talked about this a little bit before. If I flip a fair coin 5 times, what are my outcomes when I flip a coin? I get either a head or a tail. We will assume I do not have a coin that's going to land on the side. I'll assume I get a head or a tail, and we can assume maybe the coin is fair and it's 50-50, or maybe the coin is biased. And what I might want to do is I might want to let xi be the outcome of the ith toss. And so the question is, what is 2 heads plus a tail plus a head plus a tail? What does that equal? I can't really add heads and tails together, right? Physical quantities, that are different, I can't add. 2 heads and 3 heads, can I add those? Yes, that's 5 heads. So if you only get heads, not a problem. But most coins are not going to be the Mobius coin, which always lands on one side. Most coins, you're going to get heads and tails. And you want to be able to combine things. And the way we combine things is this notion of a random variable. And this is why we always have random variables real valued. By making our random variables real valued, it allows us to combine things. So if you want, we can almost call this units. So the first is random variables are real valued, so we can combine. So head plus tail, I don't know. But 1 plus 0 or 1 plus -1, that we can do. And so typically, when you're doing coins, you'll make a head a 1, and you'll make a tail either a 0 or a -1. The advantage of making a tail a 0 is if you now just sum up, you'll get the total number of heads. If you make a tail -1, you can say every time I take a head, I move 1 step to the left. Every time I take a tail, I move 1 step to the right. And then that will give me my running sum. That will give me where I am. So there's advantages and disadvantages to both methods. But it allows us to combine things. Okay? What we're doing over here, by shifting my probability distribution by subtracting off the mean, is we're trying to normalize everything. If I add 50 points to everybody's score, I've shifted everybody together. If I want to understand the fluctuations of what's going on, that part isn't so interesting. I want to understand the fluctuations due to ability or lack of sleep or whatever. And so I might want to normalize my random variables. If I change measuring things in meters versus feet, will the physical units change? If I change from measuring in meters to feet, will the physical units change? Yes. Will the actual numerical values change? Yes. 1 meter is not 1 foot, right? But if I actually look at the extension in physical space, will that change depending on the units I use? No. Okay? And so in some sense, I can make things look differently by just rescaling the axes. And it's not fundamentally different. So one of the big things we're going to be doing in class is we're going to be standardizing the random variables. Think of it as always, you want to compare apples and apples, not apples and oranges. You want to have things that are equivalent to each other so you can combine them. And so going on over here, these moments are going to be extremely important. And so we're taking a very special case of our function g. We're taking it just to be a pure power. Or here, we're subtracting a constant and then raising it to a power. And the constant we're subtracting is a very nice constant related to the average value. It turns out that if you understand these moments, you can often understand the distribution. Now the question is, when would that ever occur? If you know the distribution, don't you know the moments? You can just do the calculation. So if you know the distribution, in some sense, you know the moments. Remember when we did the Fibonacci numbers, when we had the massive linked lecture, and we wrote down the generating function? To me, this is a miracle. We start off with the recurrence relation for the Fibonacci's. We somehow bundle them together into this generating function, and then we are able to extrapolate and cull out the actual values for the nth Fibonacci numbers, and then get a beautiful closed form expression, Binet's formula. The reason we can do this is as soon as we know the recurrence relation for the Fibonacci's and the first 2 Fibonacci's, do we know everything? Yes. Do we know everything in a pleasant way, where if you ask me for the billionth Fibonacci number, I would say, oh, sure, no problem. The billionth Fibonacci number, it's the following. No. It would be a painful calculation, but as soon as we know the recurrence and the first 2 values, we know everything. In some sense, if you know the density, should you know the moments? Yes. It may be an integral like the one I erased over here that I can't evaluate in closed form, but in principle, if you know the density, should you know the moments? Okay, so this should suggest a converse question. So if you know the density, you know the moments. What's the converse question?
If you know the moments.
If you know the moments, do you know the density? What do you think? So this is one of the big questions in probability. Can you have two different distributions that have the same moments? This is the reason why real analysis is a hard subject and complex analysis is an easy subject. Complex analysis is the most discriminatory of all subjects in mathematics. It does not let bad functions in. If your function is complex differentiable, it turns out this means an enormous wealth of things happen. Real analysis is the very inclusive, open subject. It will let any function in no matter how bad it is. And just knowing that a function is continuous gives you very little. It turns out almost every continuous function is differentiable nowhere. Functions that are just real differentiable, they don't have nice properties in general. But a complex function that's differentiable once has the following properties. If you're differentiable once, you're differentiable infinitely often, and you equal your Taylor series expansion. There are a lot of functions of one real variable that are not differentiable infinitely often. It's a very different subject. What's going on at a fundamental level is if you're complex differentiable, Stokes' theorem is lurking in the background. So all that stuff at the end of Calc 3 that sometimes gets rushed to, this is where it comes in and pays dividends. It allows you to analyze a lot of these things. The question is, if I know the moments, do I know my distribution? The answer is sadly, most of the time no, but sometimes yes. And in some sense, this is one of the avenues that we'll use to get to the central limit theorem. We will have some observed values. Maybe I'm going to be rolling my die, and I'm going to keep rolling it. I'll roll it once, twice, 3 times, 4 times, 5 times, 6 times. I'll keep increasing the number of rolls, and I'll keep summing all those rolls together. The central limit theorem says that as you roll it more and more often, as you sum it, if you appropriately normalize it, it's going to converge to a Gaussian. One of the ways we'll do this is we will calculate the moments of the sums of the rolls. And we'll show that the moments converge to the moments of the Gaussian. And then we will invoke some black box results from complex analysis and say that it now must be converging to the Gaussian. So that's the part of the class that, in the first course in probability, we probably will not get time to do. But if people are interested, I'm happy to have either additional lectures or the stuff in the book about the basics of complex analysis you need to finish the proof. But it's always nice to know where's the meat, where's the beef, where is the deep part. The deep part is going in the other direction. Knowing the moments, when does that allow you to know the distribution? The real difficulty is you should all be conditioned now. In this equation here, what is f of x? The density of the random variable x. And what is n? What's n? The moment we're looking at. What kind of number is n? Integer, because I always use n for integer. This is the difficulty. We're only calculating a discrete set of moments. The result we need from complex analysis is we need to replace this n with the letter r. And we need to be able to calculate moments in an interval. And so I'll talk more about that later. But one of the problems in the subject is if you only have a discrete set of data, that's where you can have indeterminacy. The situation is very different if you have a discrete random variable that takes on only finitely many values. It turns out if you only take on 6 values, you only need 6 moments. If you take 8 values, you only need 8 moments to uniquely determine the distribution. But in general, things are a little bit harder. So again, the reason we're going to care so much about this is by using the moments, we'll be able to prove things like the central limit theorem. And again, if I know the distribution, it's not so important to calculate most of the moments. But if I don't know the distribution, if I'm looking at sums of rolls of die, so you should have done hopefully the reading and seen just sums of 2 die is not so bad. If you remember what we did in that joint lecture, I wrote down the density function for sums of 4 rolls of die, and it was a monster in terms of all the different split cases and the values. To go beyond that and write things down in closed form is a nightmare. The fact that it's converging to a normal, which has a really nice density, that's a huge advantage. So this is one of the reasons why we care about calculating moments. Now, one of the problems, of course, is whether or not these moments exist. And so this is a good time to talk about the Cauchy distribution and normalizing constants. So let's consider f of x is 1 over 1 plus x squared. Is this a possible probability distribution? Does it have a chance? Yeah, it's non-negative, but does it integrate to 1? No. It unfortunately integrates to pi. Well, if you integrate to something that's not 1, as long as you don't integrate to 0, I can fix it. If you integrate to 5, what should I do? Multiply by 1/5. If it integrates to 12, multiply by 1/12. So here, oh look, somebody left some space. Multiply by 1 over pi. And that is now going to be a probability distribution. Now the question is, why does this work? So the derivative of arctangent of x turns out to be 1 over 1 plus x squared. And so I'm not going to go through all the calculations. I'll just give you a quick sense of where this comes from. What is the tangent of arctangent of x? X. All right. I want to take the derivative of both sides. I'll let you guys do one side of the equation. Which side do you want to take the derivative of? All right, what's the derivative on the right-hand side? 1. All right, I'll do the other side. So we get tangent prime at arctangent of x times arctangent prime of x equals 1. Well, we know the derivative of tangent. It is it's 1 over it's secant squared or 1 over cosine squared. Okay, we know what the derivative of tangent is. If not, you can use the quotient rule. Calculate the derivative of tangent, put it in arctangent of x, and now we can solve for arctangent prime of x. And what you want to do is you want to draw a little triangle, draw a right triangle. So arctangent of x, I'm talking about an angle theta whose tangent is x. Well, if I want the tangent to be x, I could make this side be x, this side be 1, and this side would be 1 plus x squared square root. So the cosine of this angle would be 1 over the square root of 1 plus x squared. And so I'll leave you to finish the algebra. This is a nice way of using the chain rule. We now know that the derivative of arctangent is 1 over 1 plus x squared. If I want to integrate that, I can integrate this. And now you just play the games. Instead of integrating from minus infinity to infinity, I could integrate from 0 to infinity and double. And then this will prove that this is a probability distribution. This is one of the most important observations in probability, this idea of normalizing constant. That if you have something that is non-negative and has a finite integral, you can fix it by multiplying by the appropriate value. We are going to get enormous dividends of this later. How many of you remember your polar coordinates? Oh, all right, spherical coordinates. I won't even look to see which of my students are raising their hands. All right, hyperspherical coordinates, the coordinates on a 4 sphere. On the n sphere. You can bypass a lot of those horrible coordinates by the theory of normalizing constants by saying, well, it's got to integrate to 1 because it's a probability distribution. I can pick off what things have to be. You can bypass some very nasty change of variables, and you can calculate for free things like the volume and the surface area of the n-dimensional sphere. So we'll see some great applications of that later. This idea of normalizing constants, this is not an isolated example. This is huge. All right, so we're talking about the Cauchy random variable. What do you think the most natural question to ask about a Cauchy random variable? I'm sorry? Well, we've got its density. Now that we have its density, I'm going to assume that everybody's grade on my exam is coming from a Cauchy random variable. Some of you are going to be getting negative scores. Some of you are going to do damn well and have incredibly large scores. What might you want to know? Pretend you're medical school students. The average, right? Medical school students always want to know what is the average. How am I doing relative to the mean? Right? So we would want to calculate the mean. So it's the integral from minus infinity to infinity of x times 1 over pi 1 over 1 plus x squared dx. What does that integral equal? So what should this integral be? What kind of function is the integrand?
It should be x tangent of x from negative infinity.
Well, no, because what kind of function is this? It's symmetrical zero. It's an odd function. What should the integral of an odd function about 0 be? Doesn't it matter? I mean, if you look at the plot of this function, when x equals 0, we have 1 over pi. As x gets larger, it's getting smaller. So maybe something like this. Here's my Cauchy distribution. It's decaying roughly at the rate of 1 over x squared. It's symmetric about the origin. So you're just as likely to have a low negative score as a low positive score, a high negative score, a high positive score. The mean should be 0. The problem is we have to ask, well, what do we mean by the integral? And this is where the subject is a lot more technical than you might remember. We're now going to infinity. Whenever you see an infinity in mathematics, there should be a danger sign. Is this well defined? And so how many of you in your calculus classes talked carefully about indefinite integrals? Or was this basically just glossed over? Okay, it's almost surely glossed over. So indefinite integrals. So let's look at the integral from minus infinity to infinity of f of x dx. This is the limit as a and b go to infinity of the integral from minus a to b of f of x dx. So I allow the endpoints to go to infinity any way they want. What do you think is a really good way to go to infinity for the Cauchy distribution? I want to relate a and b. How should a and b be going off to infinity? The same rate. So for Cauchy, if I take b equals a, I get the integral from minus a to a, x times 1 over pi 1 over 1 plus x squared dx. Take the limit as a goes to infinity. What will that integral equal? It's going to be 0. This is an odd function. OK, the Cauchy has mean 0. Well, let's try another path. Let's try b equals 2a. And now we get the limit as a goes to infinity, the integral from minus a to 2a of x times 1 over pi 1 over 1 plus x squared dx. Well, if I want to look at this integral, the integral from minus a to a is 0 by symmetry. So this is the same as the limit as a goes to infinity of the integral from a to 2a of 1 over pi. I'll pull out the 1 over pi. And then I have x over 1 plus x squared dx. When x is really, really large, what does x over 1 plus x squared look like? I'm sorry? It does look like 0, but we want to be a little bit more accurate than 0. It looks roughly like 1 over x. The error is going to be really small. It's essentially 1 over x. What's the integral of 1 over x? The antiderivative of 1 over x. Natural log. So the integrand of this is natural log. So I get the natural log of 2a minus the natural log of a. The log of a difference is the quotient of the logs. So this is going to look like the natural log of 2. And then as a goes to infinity, this actually converges to the natural log of 2. And you can do a little bit of work and show that your error is not that bad. Or you could say, well, it's going to be at least 1 over 2x when x is large. And you can say it's going to be greater than 1/2 log 2, if you want to do a little bit more work. The point here is that by going to infinity a different way, we get a different answer for the mean. In fact, whatever you want the mean to be, I'll go to infinity in such a way to make that the mean. We say that the Cauchy distribution does not have a well-defined mean. We also say it has mean 0. Informally, come on, it looks like it has mean 0. But the higher moments definitely don't exist. If you try to calculate the second moment, the integral of x squared times the Cauchy density, that will clearly blow up. Why will that blow up? Well, if I come over here, if I now take the second moment, if I now calculate x squared, well, when x is really large, what does the integrand look like, approximately? 1 over pi. So we can argue however long you want as to whether or not the Cauchy distribution has a mean. I don't mind being swayed to say it has a mean 0. But when we get to the second moment, there's no argument. It does not have a finite second moment. There it's because of convergence issues. There's a difference between integrating with the even moments and the odd moments. The even moments are always non-negative. You don't have to worry about cancellation due to sign. For the odd moments, you actually have the possibility of cancellation due to sign. So the Cauchy distribution, there's a lot we can learn from it. There's a huge amount of work being done on the Cauchy distribution now in terms of how you should model the real world. And there's a lot of people who say that the Gaussian and the uniform, the Gaussian and random walks, these central limit theorem arguments, these are not good models for the real world. They do not give high enough probabilities of unlikely events. The Cauchy distribution decays very slowly compared to the normal. The normal decays like e to the minus x squared. It's decaying faster than exponential. The Cauchy distribution decays very slowly, and so it actually assigns reasonable probabilities to high events. And so we'll see later in the semester some good applications of the Cauchy. All right, so why am I so gung-ho about moments? So I've been telling you that it's supposed to be the reverse. If you know the distribution, you know the moments. If you know the moments, hopefully you know the distribution. This should remind you of something from Calc 3. Sometimes people do this in Calc 2. This is Taylor series. Okay? So Taylor series are extremely useful. And the idea of Taylor series is to take a complicated function and replace it with a simpler one and control the error. So I quickly review Taylor series in the book. We saw this, I think, early in the semester when we were looking at the birthday problem. We had to take the log of 1 minus x where x was small. We used the Taylor series formula to expand it and get a good estimate for the probability. So the Taylor series of order n of a function f at x would be f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial x squared plus dot 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 plus the nth derivative at 0 over n factorial x to the n. And the idea is, in general, the more terms you take, the better approximation this will give to your function. It should not be a surprise that the 0th order Taylor series does a really good job of approximating the function at 0. It's by definition, right? We define the function to be f of 0. Well, okay, not surprising, it does a good job. The question is, how long of a window in each direction can I go and still have this doing a good job? How much will my error be? That's the meat. That's what we really want to understand. And the idea is that as we take more and more terms, we should be accurate for hopefully longer windows with smaller errors. So if you haven't seen the calculations before, look at approximating sine of x or cosine of x with their Taylor series. And just plot the first few Taylor approximations and see the rapidity of convergence. So here's my question for you. If I give you a nice function, I can calculate its Taylor series coefficients. What's the converse question?
Given a Taylor series.
So given a Taylor series, does that uniquely determine a nice function? And so the answer is no. So consider g of x is e to the minus 1 over x squared if x does not equal 0, and 0 if x equals 0. This is one of the reasons why real analysis is such a hard subject. Real analysis allows you to talk about a function like this. Complex analysis does not. This function is not complex differentiable. This function is real differentiable, but it's not complex differentiable. When you think about what's going on, what is the easiest point to evaluate this function? 0. Why is 0 the easiest point? Yeah, I'm giving it to you. I'm telling you it's 0 at 0. All right? That should be the easiest point. Let's say we move a little bit away from 0. So if we move a little bit away, we're at a very small number. I'm going to write my number as maybe 1 over n, where n is a huge number. Well, if x is 1 over n, x squared is 1 over n squared, the reciprocal of that would be then n squared. This would be e to the minus n squared. E to the minus n squared is going to be very close to 0. So if you plot this function, it's going to look something like this. It's going to be so indistinguishable from 0. It turns out, if you calculate all the derivatives of this function, every derivative of this function at the origin exists and is 0. The way you prove this is you use L'Hopital's rule and the definition of the derivative. So L'Hopital plus definition of derivative implies that the nth derivative of g is always 0. Oh dear. What does that give us for the Taylor series expansion? Its Taylor series expansion is identically 0. So g's Taylor series are always identically 0. This is disastrous. And it's disastrous for more than just the fact that, well, okay, I'm never going to look at this function. I promise Professor Miller I will not look at this. What if I give you the function h of x is sine of x plus 1789 g of x? If you calculate the Taylor series expansion from this, or you calculate the Taylor series expansion of I of x equals sine of x, can you distinguish these two functions by their Taylor series? No. A Taylor series does not uniquely determine a function. That should be a very unsettling result, because we talk about how great Taylor series are. A Taylor series is not going to uniquely determine the function you're looking at. We need additional information for that to happen. So again, this is a first course in probability. This is a course before real analysis. This is a course before complex analysis. I hope many of you have either already taken some of these courses or will take these courses eventually. I'm happy to talk more about some of these stuff. I want to get some of this stuff on your radar screen. For those of you who haven't taken real and are hopefully going to take real, this will hopefully motivate. Is that enough hopes? This will hopefully motivate why you will spend all this time in real caring about these technical issues. We need that to make this subject work. We have to worry about these integrals making sense. We have to worry about convergence. We have to worry about non-uniqueness. These are horrible issues. Okay, so this is a good place to stop.